So in the vapor pressure formula, you have the mole fraction of the solvent. The mole fraction of the solvent does include the I constant, the Van Hoff factor. You're going to take the I and multiply that moles by moles of the solute. I can't spell. And then add that back to moles of the solvent from above. The reason again for that is that dissociation. For example, calcium chloride, for every 1 mole of calcium chloride, you have 3 moles of particles. Because you have 1 mole of calcium and 2 moles of chloride. So that's why if you have the moles of the solute, the moles of calcium chloride, you got to multiply it by that 3 to get the moles total. Because that's what the mole fraction says. It's moles of solvent over total moles of particles. And then the other formula here is osmotic pressure. And that is pi equals I molarity RT, with that R constant being whatever you want the pressure to be in. Don't forget, since you have that R constant, you need to make sure your temperature is in Kelvin. Solute, thing that is dissolved. Solvent, thing that does the dissolving. Saturated, the amount that you could possibly have dissolved. Miscible means they can mix. Immiscible means they can't. Unsaturated means you have less than the maximum amount that you could have dissolved. Supersaturated means you have more. A colloid and suspension, these are termed from last semester actually. A suspension is whenever the particles are bigger and they can be affected by gravity. That is a suspension. The example we used last semester all the time was chocolate milk. If you allowed the chocolate milk to sit out, like Hershey's chocolate milk or something like that, eventually you would get a dark layer at the bottom, and then the milk would become pure as you went up. That's because the particles that were suspended are now pulled down by gravity. A colloid would be more like toothpaste. It doesn't move. You don't have to shake it up. They just stay in there. Tyndall effect is basically the scattering of light. And that's going to be a big part of this Spec 20 lab. Scattering of light due to dissolved particles. Let's take a look. Here I've got some ordinary tap water. And here I've got some light. You can see the light faintly through this tap water. If this were distilled water, you would not see that light going through the water itself. You wouldn't see it. That light is there because, well, somebody might say the school water is nasty, but it's also there because there are particles in there. So you can actually see that laser light through there at some times, right? Looks like right now, maybe the particles have settled enough. Oh, there we go. Watch this. Let me go ahead and I'm going to introduce some silver to it. And if we remember from last semester, silver will react with certain things to become solid. What we're going to create is a suspension. I've got some silver nitrate. I'm just going to put 1 drop in there. That should be enough. Did I get a drop? There's a drop. Put that silver nitrate in there. Oh no, my laser light's dying. Come on, you. Now we can see, come on, laser light. I'm gonna have to get a different battery. That's sad. What type of batteries do these take? Oh, there's some double A's right there. Big, quick switch out. There we go. Now you can see that light very good. That's because of the silver chloride from the chlorine in the water. That silver chloride is actually suspended. If we let this sit for a few seconds, all that silver chloride will go to the bottom, and then we'll be back to where we were before.
Wait, Mr. Jackson, I have a quick question.
Yeah.
So if there's no like solute particles, we'll be able to, there's no scattering of light, but if
Got
like
it.
we added the silver, there's a scattering.
Mm-hmm.
Okay.
And that is a Tano effect, yep. So formulas for molarity, that's basically what you did on Monday, or last Friday, I should say, right? Most of you. This is from when we talked about the chicken wings. Likes dissolve lights. It's a video of the boy who tried to make the seltzer wine. Also, hot tea versus cold tea with sugar. Dissolution of ionic, that is the Van Hout factor versus molecular. Molecular solids always have one particle. Interpret and apply the solubility curve data. That's the worksheet I graded. Some of you might want to check that because there were grades that were less than perfect on that. Lab information, and this is what we have left. So let's just play a quick game. Let's do a few of these nice questions right here that look quick and easy. Is this polar, non-polar, or ionic?
Ionic.
So that means it's dissolving in what?
A polar solvent?
Yeah, polar. Good. Polar, non-polar, or ionic?
Non-polar.
Non-polar, so it only dissolves in non-polar solvents, right? You do the same thing for the rest of them. Which compound solubility is most affected by temperature change?
A.
A. As the temperature increases, A goes, whoop, right? Skyrockets. Most affected. Could the one that goes down be most affected by it? If it were a different line, I'm just saying, could one that goes down be more affected by it?
Yeah.
Yeah, right? Why couldn't it go like this or something, right? Yeah.
Oh, did you mean to put the A in the first line?
Yeah, I did. I haven't gotten to B yet. Which of the four compounds could be a gas?
C.
C for sure. Because as we increase temperature, solubility decreases. If you determine the solubility of each substance at point X, this is a hard concept. Some of you guys mix this up on the homework. So basically what I'm saying is if each of these substances A, B, and C were at X, that point right there, do we have more C than we should? If this is a line for C and we are here, do we have more C than we normally would be able to hold in there?
Yep.
Yeah. So if this dot is above the line, then it is supersaturated. C would be supersaturated. Can we hold more B than this? This is the
Yeah.
point we're at. We could hold more B. Could we hold more A?
Yeah.
Yeah. So A and B are both unsaturated. And that gets confusing. If we take a look at the very front page here, this right here, instead of having multiple lines, they have multiple dots. So that means that if you're at point A, again, you always want to go with your point and then say, okay, well, if I were at point A, I could get more. So at point A, this is unsaturated. At point B, it is saturated. And at point C and D, if we were at these points, we would be supersaturated. So the actual question says, oh, label the points as saturated, unsaturated, supersaturated. So I just did that. So always keep in mind where the line is, but think about the position at the of the point. The rest is just boring math problems that we've done so many of. Until you get to, there's a, whatever these are called, word search, crossword,
Crossword puzzle.
scramble, what is it, Scrabble? When did you get to the Scrabble? That checks you on the vocabulary again. That's a good one. Because a lot of times, you know, a vocabulary question will be worth just as much as another question. This is the last thing we want to talk about, and something tells me that most of you are inclined enough with math to be able to answer this without even ever seeing a graph like this before. Let's just talk about how a graph works. On the x-axis, we have the independent variable. This is usually time. In this case, with a solution, it's concentration. And keeping the idea of that Tyndall effect, if we shine a light through a sample, right? And we had a photocell on the other side of that sample, we could find out how much light shone through it. All right, you can draw a little light bulb here. Look at that perfect little light bulb. So that is shining through. Some goes through, it's picked up by the photo sensor, and then it says, hey, this much light went through. Any light that wasn't gone, that didn't go through, must have been absorbed, right? And that's what absorbance is. Now, we talked about how you never really have seen anything in your life. You've only seen the light that's reflected off of it, right? You've never seen anything except for light, and you've only seen the light that's reflected off of it. So if we were to ask a normal person what color this is, they are actually going to tell us the color that does what?
Reflects off of it.
Reflects off of it. So light hits it, it reflects off.
Could you try again?
Nope. Light hits it, it reflects off the blue wavelengths. Since this is a room filled with white light, that means all of the other wavelengths must be being absorbed. So that means certain wavelengths are absorbed better. And that is the goal of Thursday. Thursday, we want to find out, we want to find the best wavelength. The best wavelength will be the one that absorbs the most. They have the wavelength for this. They don't give it to us because they don't need it. They say using the absorption plot below, if you ran an unknown sample and recorded an absorbance of 0.390, you would approximate its concentration to be blah. Well, what we're going to do is we're going to find the best wavelength for the light that your solution works in. What color was your solution?
Red.
It's like red.
Yeah. Do you think that that would be, that red would be the best to shoot at it then?
No.
Well, we said that it would reflect red, right? Versus absorbing red. Because that's what we see when we look at it. We'll find more about that out when we find the wavelength, but red probably would not be the great one. So whatever one they found here, if they have no solution in there, then how much absorbance is there?
0.
0, right? So that's a point that must be on your graph. 0, 0, the origin. Then they did 1, 2, 3, 4, 5 trials. All of those trials, they knew the molarity for because they knew the initial concentration of their solution. What was the initial concentration of their solution most likely? Oh, this is a hard one. This might be a student of the month question in here.
What was the question?
What do you think their initial concentration that they started this was? Let me ask you this. What's your concentration that you're starting it with?
0.200 mole. Or
Right? 0.200. Is it going to be easier to lower that concentration or to raise that concentration?
probably raise. Actually, no, lower it. Lower it.
Lower it. What is that called when we lower the concentration of something?
Making it more dilute.
You got it. We're diluting it. And we have a whole formula for that kind of thing, don't we? Right? So that's going to be easy. We're going to be able to add more solvent to that easier than we would to find the new concentration by adding more of the powder. So they probably started with a concentration of 0.0120, and then they diluted it to these different ones. You're going to do the same thing. That means you'll get this point first, and then you'll work your way back to 0. You'll want to put this on a scatter plot, Excel, concentration to absorbance, and then you'll want to do a best fit line, right? You can do this by hand if you want. I have kids do it by hand every year. Up to you. I don't know if that's easier with digital or not, but yeah, I think you can do it. Does it make sense that as the concentration increases, the absorbency increases?
Yeah, because there's more particles. Per,
Yeah. More particles to scatter light and absorb it, right? So that's the idea there. That's a pretty big thing that you can find concentration. They say, okay, I got an absorbance of 0.39. So that's about right here. 0.39. Well, the way you read a graph is you go over to the line because that's my y and this is my x. So what's my x? 0.006 something. Is it 0.0045? No. Is it 0.0055? No. Is it off the scale? I don't think so. 0.0067. One of the things you guys want to do is I'm going to give you 3 unknowns, and one of those unknowns will actually be higher than 0.2000. What does that mean? You will have to extrapolate your graph past this point. You can do that one of 2 ways. You could sit there and calculate a point on that best fit curve line way up here, and that will make your graph bigger. You can find the line value and plug in and figure it out that way. Either way is fine. If you find the slope of this and then put it in slope line form, then you could find that. Questions? All right, so I'm going to go ahead and show you the instrument. These instruments are actually older than me. It's funny, we were talking, where's I talking to? Jake Berther, he's a tennis player, pretty cool kid. I think he's a senior this year. But he was laughing at me and asked me what I was doing this weekend. And told him I was playing video games. He asked me for my gamer tag, and it dawned on me that my gamer tag is older than Jake. I don't even know how you guys have gamer tags. You have to put like silly letters in there or something weird now, right? This thing is older than me. So if we take a look, this is an analog machine. Can you guys see this okay? I'm still sharing, aren't I? Is this in the share or not?
No.
It's showing like a black screen.
All right, you don't want that. How's this?
Yeah, that's better.
Ooh, right. Oh, you guys are using a chat. Why would you do that? I never see the chat. I can't even read it. Decently laggy. Is it very laggy? Is his screen frozen? Okay. Are you better now? Tell the chat. All right. So hopefully you guys can see every aspect of this. This is a machine. To turn it on, you go like that. This machine needs to run for 15 minutes before, so I will actually probably turn all of these on before you guys get in here. Can you see these letters? For some reason, I need to pin myself. How do I pin myself? There we go. Can you see these letters? I don't think you guys can see that decimal point. But this is 0.1, it says. Looking for something, maybe I can boost it up a little bit more. How's that? It's a little bit of a glare.
It's better.
The glare is gone. All right, cool. So here is the instrument. This is called a Spectronic 20D, or Spec 20 for short. This is Milton Roy. I have no clue if that company even exists. There is a light bulb here under this, and that is going to shine light this way. It's going to shine it through a slit, and I can adjust that slit, changing the wavelength. So that's 484 nanometers, 467, 453. I'm going to do 450 to start with. Notice I have to turn this knob. If this knob feels rough, stop turning it. You've done something wrong or the machine is broken. If you turn it too much, you'll end up breaking it more. Currently, there's nothing in here. I am looking at transmittance. And since there's nothing in there, we should be at 0 transmittance. So I turn the 0 button until that gets to 0. You can see it flashing there. I rather would not have it flashing, but it is better than that if it's flashing, because that means I'm really close to 0. You can see it's got a little bit of play in it, but you should be able to get it right on that 0 or real close to it. The next thing you need to know about is something called a cuvette. It looks like a test tube, but it is much smaller. Please do not put these in any drawers because these are more expensive than test tubes, even though they're smaller. This cuvette right here is called my blank. So I am going to wipe my blank. And then I'm going to put it in. Notice there is a symbol on there. There's also a line here. I'm going to drop that right into that machine. And now it is shooting light through that. What was my solvent used for this laboratory?
Water.
Distilled water. So that right there, blank, needs to have 100% transmittance, because I don't want the distilled water to have any factor on it or the glass that is around it. That glass can change the distilled water. So that glass can, and if there's any impurities in that distilled water, can make that different. So I want to bring it up to 100. So notice I'm using the 100 now. This is the 0. That's how I got it to 0. This is the 100. Oh, go back, you. Yeah. How many of you have anything analog like this at home? Most of the stuff is digital, and we'd be able to press a button and say, it's at 100. Right? Not so much with this. We have one even older than this one, which has just a dial. I can pull that one out if anybody wants that. Come on, you. Maybe because it's not warmed up. One little more. All right, so then we are going to pull out the blank because now it's at 0, a little more, and 100, 0, and with the blank, 100. So the equipment is now set. Oh, you son of a gun. That's probably because it is warming up. So as the bulb gets hotter, it's going to change things a little bit. That's why we run them at 15 for 15 minutes before. We don't have time to sit around here for 15 minutes. With the best thing, what we would do is we would use the same piece of same cuvette. I'm not going to do that right now because I'm just showing you this. And notice I'm always wiping off fingerprints and stuff just in case. But we have to use a different cuvette, so we want to make sure it's the same company because there will be imperfections there. That would give us air. If you did use the same cuvette, you would reduce your air, but you're also going to increase your time. So that is the transmittance of that solution. I don't want transmittance because my graph is not from concentration to transmittance. So I need to change the mode. I want absorbance. I change the mode and I'm at 0.316. So that would be my absorbance at 450 nanometers. So then I'm going to pull that out. And on Thursday's lab, it's quite boring. You are going to change the wavelength from 450, and we are on absorbance, so I want to get back to transmittance. That'll be a big mistake for people. 450 to 470. I think you go up by 20 nanometer increments. So 470, look at this, very cool. Our transmittance is 0. Let's get our blank out because you have to do this every time. And we pop our blank in. Either the heat of it or the wavelength has changed the blank. So I need to get that back down to 100. And this is the one that I had the most trouble with last time. So hopefully I can get it a little bit quicker this time. We shall see. And again, remember, never force this thing. If it feels like you can't turn it, then you probably should not be turning it. Oh, you son of a gun. Such small little turns. And we pull out the blank. And again, we pop in our thing. What was it last time? 0.318 or something like that?
It was like 0.316.
So remember, now we are at 34.2% transmittance. We don't want transmittance, we want absorbance. 0.468. So is 450 a better or worse wavelength for this solution? Are we getting more absorbance now or less absorbance?
We're getting more absorbance with the 470.
You got it. So we want the highest absorbance you can get. So now you would go 490. You would see, is it better or not? And then you would go all the way up until you can't go anymore. One of the things will be, will not allow you to go further than a certain wavelength, and it's machine dependent. So just keep that in mind. Now let me ask you this. I'm going to keep it at 470. What was that absorbance one more time? 0.4. 0.46A, 0.470. Well, let me make sure I'm lined up here. .468. So there's my absorbance. I'm going to pull this out. I'm going to switch back to transmittance. I'm at 0. I'm going to put in my blank cuvette. Notice I'm using the same one. I don't need many. It's like dinner. You only need one real napkin unless you're a slob, right? Some guys are slobs in this lab. At 100. Oh, I don't even want to touch it though. There we go. Oh, come on, you. at 100. I'm going to do something different here. I'm going to basically try to cut this solution in half. I'm not using any measurements whatsoever. So just keep that in mind. And I'm going to fill this up and dilute this. What do we expect to happen to the absorbance?
Decrease.
Right? So again, I wipe this off. And I know I did not use any measurements, but since I tried to get it in half, we would expect the absorbance to be, what were we at before? 4.6 something? Yes, yes. 0.46 something, was it? And about half of the concentration, we are at half the absorbance, 0.228. Questions there?
So is transmittance like the measurement of how much light goes through?
You got it.
Absorbance is like how much the particles absorb?
You got it. That's exactly it. Good. Those are the only two things that we're going to deal with. But yeah, so that's 59% light going through with a 0.229 absorbance. Cool little old machine. The biggest thing is to make sure you take out that last one. Because if you don't take it out and somebody tips this machine, that liquid will leak into this and do damage to it. These are older than me, right? So that means they've been well taken care of. And again, don't twist the knobs all willy-nilly. What's the old, it's kind of funny. I don't even know if it means anything to you guys, but they used to say whenever you're in the radio, you got in the car and there was an awesome song on, you'd be like, crank it up. That's that thing. You'd have to turn that, up. Crank on it. Questions there?
When is our test for this unit?
Monday is what I'm looking at. So tomorrow I'll take any questions over the review or the laboratory. Thursday, you guys will come in and do the laboratory. And then Friday, you'll come in and finish the laboratory. Test Monday.
Will you post the answers to the review?
Yes.
Okay.
I'll try to get those up by the end of the day today. Any other questions? No. All right. If you guys do have questions that you didn't want to ask before,